At the heart of our galaxy lies something immense and invisible, a supermassive black hole known as Sagittarius A. It bends, space swallows light, and shapes the Milky Way itself. But how does something we can't see control everything around it? Stay tuned as we uncover the mystery. If you enjoy this, please like, subscribe and share, and tell us in the comments, what do you think truly hides beyond its event horizon? Thank you for watching. Now, let's begin. The Milky Way stretches across the sky as a pale ribbon of light, the collected glow of hundreds of billions of stars arranged in a vast spiral disk. From far outside, the galaxy would appear as a soft swirl, its arms tracing gentle curves that wind inward toward a denser core. The spiral arms are made of young blue stars, glowing gas and dark filaments of dust that trace the paths of gravity through the galactic plane. Between them, great lanes of emptiness widen before converging again toward the crowded center. The entire disk rotates slowly, each star following its own elongated path through the gravitational field that binds the galaxy together. This rotation takes hundreds of millions of years to complete a slow and silent movement that defines the galaxy's structure. From the position of the solar system about 26,000 light-years from the center, the inner region cannot be seen directly. Dust and gas fill the plane of the galaxy, scattering and absorbing visible light. The thickening layers toward the middle create a hazy barrier that hides the core from ordinary sight. Yet the overall shape of the galaxy can be inferred from motion and light. The disk is about 100,000 light-years across, and only a few thousand light-years thick, with the central bulge rising above and below the plane like a rounded glow. Within this bulge lies the densest concentration of stars in the Milky Way, a region where gravity grows stronger and the interstellar environment becomes more extreme. The bulge itself is not uniform. It contains both ancient stars formed billions of years ago and younger ones born in more recent bursts of star formation. The mixture of ages and compositions suggests a long and complex history, shaped by the accumulation of matter and the slow merging of smaller galaxies. Moving inward through the bulge, the brightness increases as countless faint stars overlap into a diffuse golden haze. The light is steady and warm, a collective radiance that hides the violent interactions occurring among its sources. In this region, stellar density can reach more than 1,000 times that found near the Sun. Collisions and close encounters between stars are still rare but no longer impossible. The gravitational field becomes crowded and uneven, constantly shifting, as clusters move and gas clouds drift through the volume. The central region of the Milky Way acts as both the anchor and the engine of the galaxy. It stabilizes the orbits of the outer arms and influences the movement of gas and dust through the disk. Radio observations show that the entire system rotates around a common center of mass located deep within the bulge. This point marks the location of Sagittarius A star, the dark gravitational focus of the galaxy, though it cannot yet be seen. What can be measured instead is the motion of everything around it. Stars near the core move rapidly, completing their orbits in only a few years or decades, rather than the hundreds of millions required in the outer disk. This acceleration indicates the presence of a massive but compact object hidden from view. The gas and dust of the inner galaxy flow toward the core along elongated orbits compressed by the collective gravity of the bulge. Spiral arms continue inward as faint ridges of higher density feeding material toward the middle. Along the way, star formation bursts into life where gas clouds become dense enough to collapse. These newborn stars heat and stir their surroundings, releasing winds and radiation that sculpt the environment. Yet despite this activity, the overall appearance remains steady when viewed from a distance. The light from billions of stars merges into a constant glow that defines the galactic bulge as the Milky Way's shining heart. Infrared and radio telescopes reveal structures hidden behind the optical haze. They show lanes of dark dust cutting through glowing clouds, dense knots of molecular gas, and streams of material stretching inward. The magnetic fields within the bulge align along narrow filaments that thread across the central region, guiding charged particles through space. Each thread traces an invisible current of energy that extends for dozens of light years. These filaments mark the presence of strong magnetic forces and high-energy electrons conditions that intensify closer to the core. From Earth, the direction toward the galactic center lies in the constellation Sagittarius. When astronomers first mapped this region in the early 20th century, they discovered an intense source of radio emission, now known as Sagittarius A. Subsequent observations resolved it into multiple components, including a compact central object later named Sagittarius A star. The light that reaches Earth from this region has travelled for tens of thousands of years, crossing the dusty lanes of the Milky Way before arriving in the detectors of modern observatories. Every wavelength reveals a different layer of the inner galaxy. Radio waves trace the cold gas and magnetic fields. Infrared light shows the hidden stars, and X-rays uncover high-energy interactions near the core. The galactic bulge, though visually smooth, contains structures on every scale. Massive star clusters orbit within it, some containing hundreds of thousands of stars bound by gravity. Between these clusters, diffuse gas fills the space, enriched by the remnants of countless supernova explosions. Elements forged in earlier generations of stars have mixed through the region, creating the heavy elements necessary for planets and complex chemistry. The bulge is in this sense both ancient and continually renewed. It preserves the oldest components of the Milky Way while remaining active at its center. The balance between stability and activity defines this zone. Gravitational forces keep the entire structure bound, while energy from stars and supernova drives turbulence and motion. Dust absorbs visible light, but re-radiates it in the infrared, cooling the gas and allowing it to settle into new clouds. Over millions of years, these clouds drift inward under the influence of the galaxy's central gravity. Some will fragment and form new stars, others will continue to spiral toward the unseen heart, adding to the slow accumulation of matter around Sagittarius A star. Even without direct observation, the influence of the core can be traced through the motions it creates. The stars nearest to the center move with extreme velocities, revealing the pull of an enormous mass confined within a region smaller than the solar system. This gravitational concentration dominates the inner few hundred light-years of the galaxy, shaping the orbits of stars and gas alike. Farther out, the influence weakens, but the pattern of rotation remains linked to the center, demonstrating that the Milky Way functions as a connected whole. From the quiet vantage point of the outer spiral arm, the light from the galactic bulge appears constant. Yet at its center, forces operate on scales of time and energy far beyond ordinary experience. There, within the glow of billions of overlapping stars, lies a region dense enough to bend light and distort the paths of matter. The journey inward has only begun. The next layers conceal environments where radiation thickens, temperatures rise, and magnetic structures twist in patterns that hint at the presence of the supermassive object deep within. For now, the view remains at the scale of the entire bulge, the immense spiral heart of the Milky Way turning slowly through cosmic time. The galactic plane stretches as a thin luminous band encircling the sky, filled with the overlapping light of billions of distant stars. Through telescopes, it appears not as an open field of points, but as a continuous fabric of brightness, woven with dark streaks of interstellar dust. These shadows are not empty but dense regions of carbon silicate grains and frozen molecules that absorb visible light, concealing what lies beyond. Toward the center of the Milky Way, this obscuring material thickens until even the brightest stars vanish behind veils of smoke-like haze. The path to the galactic heart runs directly through this labyrinth of gas and dust known as the galactic plane, where conditions grow more crowded, more turbulent, and more opaque with every light year inward. The material that forms these dark lanes was born from earlier generations of stars. Over billions of years, massive suns lived, died, and expelled their outer layers into the interstellar medium. The combined debris from countless stellar lifetimes accumulated into enormous clouds that now coil along the spiral arms. In the outer disk, these clouds remain relatively diffuse, but closer to the center, they are compressed by the combined gravity of the bulge and the rapid rotation of the inner galaxy. The result is a thick, luminous belt filled with giant molecular complexes, glowing nebulae, and regions of intense star formation. The gas density here can be hundreds of times higher than in the outer regions, and temperatures vary sharply between the cold interiors of molecular clouds and the hot envelopes heated by radiation from newborn stars. Through visible light, the galactic plane near Sagittarius appears as a dimming glow cut by black rifts. Yet in radio and infrared, the same area bursts into structure. Wavelengths longer than visible light can pass through dust, revealing intricate patterns, filaments of ionized gas, supernova remnants, expanding like faint shells, and clusters of massive young stars still shrouded in their birth clouds. The light that escapes from these hidden regions travels through layers of material, each scattering and reddening it, until only the longest wavelengths remain detectable. This is why observations near the galactic center rely on infrared and radio telescopes positioned high above Earth's atmosphere or in space, where the air does not block the faint signal. The energy within the plane is not evenly distributed. Magnetic fields thread through the interstellar medium, guiding charged particles along invisible lines that stretch for hundreds of light years. Cosmic rays, fast-moving atomic nuclei produced by supernova explosions, spiral along these fields, colliding with gas and producing diffuse gamma-ray emission. These high-energy processes give the galactic plane its complex glow when viewed across different parts of the electromagnetic spectrum. The brightest regions mark places where gravity and pressure combine to trigger new star formation. The darkest regions indicate clouds so thick that even infrared light struggles to escape. As the view draws closer toward the central tens of light years, the confusion deepens. The line of sight crosses multiple overlapping structures at different distances, all projecting onto the same patch of sky. This makes mapping the central region a challenge. Astronomers have developed methods to untangle this projection, using the Doppler effect, measuring how wavelengths shift due to motion along the line of sight. By analyzing these velocity patterns, they can separate near and far components and build three-dimensional models of the central plane. These studies reveal that the gas is not arranged randomly, but flows along elongated orbits shaped by the gravitational potential of the galaxy's bar, a vast stretched structure of stars that funnels matter toward the center. The bar acts like a conveyor drawing gas inward from the inner spiral arms. At its ends, the material curves into a ring-like formation surrounding the very core. This ring, known as the central molecular zone, lies hidden behind much of the dust in the galactic plane. Before reaching it, the journey passes through intermediate layers where temperatures rise and the balance between gravity radiation and turbulence becomes unstable. Shock fronts form where gas streams collide, creating dense knots that will soon ignite into stars. Elsewhere, stellar winds from massive stars carve cavities into the surrounding material, blowing bubbles of ionized gas that overlap and merge into larger cavities. When observed from radio wavelengths, these cavities and filaments weave together into a tapestry of structure that defines the inner few hundred light-years of the Milky Way. The plane glows in complex colors depending on the observed frequency: bright hydrogen emission, traces regions of ionized gas, carbon monoxide emission, outlines molecular clouds, and synchrotron radiation from high-energy electrons mark zones influenced by magnetic fields. Each component moves at a different speed and direction, revealing a restless layered environment. Beyond the aesthetic complexity lies an essential function. The gas and dust of the galactic plane are the raw materials for future generations of stars and planets. They carry the chemical elements forged in earlier epochs and distribute them throughout the galaxy. The center, where densities are highest, serves as both a graveyard for stellar remnants and a cradle for new suns. Supernova explosions inject energy that stirs the interstellar medium, preventing it from collapsing all at once. Over time, gravity reasserts control, drawing some of this matter inward toward the hidden core. The opacity of the galactic plane once made it seem impenetrable, but technology has opened it to study. Infrared surveys from space telescopes such as Spitzer and Herschel, along with radio observations from ground arrays like ALMA and the Very Large Array, have mapped its structure in unprecedented detail. These instruments reveal that what appears to be a smooth band of light from Earth is actually composed of intertwined filaments, bubbles, and sheets, each tens or hundreds of light-years across. The interplay of radiation, magnetic pressure, and gravity gives rise to patterns that shift slowly over millions of years. Yet even in their slow motion, these structures trace the flow of matter toward the nucleus, where Sagittarius A star resides. The scale of the galactic plane can be difficult to grasp. From the sun's position, it extends across the sky as a great circle, but physically it spans tens of thousands of light-years. Within a region only a few hundred light-years wide near the center, the density of material becomes extreme, creating a continuous curtain of absorption. Every photon that reaches Earth from behind this curtain carries the imprint of its passage, reddened, scattered, and attenuated. It is through this distorted light that astronomers reconstruct the inner structure of the Milky Way. As instruments probe deeper, the diffuse glow gives way to specific sources, clusters of massive stars, remnants of supernovae, and compact radio emitters near the core. Among these is Sagittarius A, a complex region containing multiple overlapping structures. Within it lies Sagittarius A star, the compact object that anchors the galaxy's rotation. But from this vantage point in the plane, it remains only a point of emission lost among many others. Its influence is seen more clearly in the motions of nearby stars and the dynamics of gas that spiral toward it, subjects revealed only once the line of sight passes fully through the dense mid-plane into the inner molecular ring. For now, the view remains dominated by the thick glow of the galactic plane itself. It is a layer where light meets resistance, where radiation, gas, and dust coexist in a delicate balance. The bright and dark patches seen across this band are records of stellar birth and death, supernova shockwaves, and gravitational currents that guide material inward. Step by step, the journey toward the center follows these threads through the crowded plane where the glow hides what may be the most massive and mysterious object in the galaxy. The visible universe ends where the dust becomes opaque. Ordinary light cannot cross the dense clouds that lie between Earth and the galactic center. For centuries, this barrier rendered the core of the Milky Way an invisible mystery. Even the most powerful optical telescopes could see only the faintest glimmer of the central bulge, dimmed and distorted by the thick haze. The inner regions seemed unreachable, hidden behind curtains of fine grains floating through space. Yet other kinds of light wavelengths, longer than those the human eye can perceive, offered a path through the obscurity. In the mid-20th century, as radio astronomy matured, scientists discovered that radio waves could pierce the interstellar dust. This realization marked a turning point. Instruments sensitive to long wavelengths began to map the galaxy in forms invisible to sight. They revealed bright sources scattered along the plane, some extended, others compact. Among them, near the constellation Sagittarius, a particularly intense concentration stood out. This was the region of Sagittarius A, and within it lay a still smaller, more compact object that would later become known as Sagittarius A star. As technology advanced, infrared detectors extended this exploration. Unlike visible light-infrared radiation, can travel through much of the interstellar dust with only limited scattering. It captures the heat emitted by stars and warm gas otherwise hidden from view. In the late 20th century, observatories such as the United Kingdom Infrared Telescope, the Infrared Space Observatory, and later the Spitzer and Herschel space telescopes transformed our understanding of the Milky Way's heart. Through their lenses, astronomers saw not a uniform cloud, but a detailed structure of filaments, cavities, and clusters. The darkness of the galactic center dissolved into a crowded, glowing landscape filled with energy and motion. Near-infrared observations revealed thousands of stars packed into the central few light years. Many were young and massive, radiating strongly in the infrared as their hot surfaces warmed the surrounding gas. Others were old giants shedding material into the interstellar medium. The overall impression was one of chaos contained by gravity. The dust, once thought to be an impenetrable wall, became a transparent medium under the right kind of light. Astronomers could now watch the core as it pulsed and shifted with stellar winds, flares, and moving gas streams. Radio astronomy continued to complement these views. Long wavelengths recorded from Earth's surface outlined the distribution of cold molecular gas and traced magnetic fields through their influence on polarized emission. Interferometric arrays linking multiple radio telescopes across continents improved resolution to the point where compact structures near the very center could be detected. Together, infrared and radio observations built a multi-layered image of the galactic nucleus. The combined picture showed not a static scene but a dynamic system with gas spiraling inward and high-energy processes shaping the environment around the unseen core. The instruments themselves became more specialized as astronomers pursued greater precision. Adaptive optics systems corrected for the blurring effects of Earth's atmosphere, allowing ground-based infrared telescopes to reach clarity once possible only from space. Observatories such as Keck in Hawaii and the Very Large Telescope in Chile began long-term monitoring of stars near the galactic center. Each observation added data points tracing how these stars moved over time. Their motions followed curved elliptical paths around an invisible focus. The curvature and speed of these orbits revealed the presence of a mass several million times that of the Sun, confined within a region smaller than the solar system. The infrared window also unveiled details about the dust itself. Instead of being uniform, it formed layered curtains of varying thickness and temperature. Some regions contained silicate grains. Others were rich in carbon compounds. Many were coated with ices of water methane and ammonia. These particles absorb light at specific wavelengths, leaving identifiable signatures that allow astronomers to map their composition. By comparing these patterns across the sky, researchers could trace the distribution of material along the line of sight, reconstructing a three-dimensional map of extinction that guides every observation toward the core. The clarity offered by infrared observation revealed that the central few hundred light-years, the region known as the central molecular zone, was far more active than the outer parts of the galaxy. The gas here cycles rapidly between phases compressed by shock waves, heated by stellar radiation, and cooled again as it radiates energy away. Each phase emits at a different wavelength, and only by combining infrared radio and submillimeter data can the full process be seen. The result is a turbulent environment where gravity, pressure, and magnetism constantly compete. It is within this restless zone that the material-feeding Sagittarius A star originates. Infrared astronomy also uncovered patterns of motion that could not be explained by ordinary stars alone. Clouds of gas orbit the center at high speeds, their paths distorted by the gravitational influence of the unseen mass. Observations at different infrared bands trace both the warm dust grains and the molecular gas mixed among them. These maps show spiral structures winding toward the nucleus, suggesting streams of material being funneled inward by the galaxy's overall gravitational potential. The process is slow on human timescales, but steady over millions of years. Space-based observatories contributed additional clarity. The Hubble Space Telescope, though primarily designed for visible light, has instruments capable of near-infrared imaging that penetrated part of the dust toward the center. Later, the James Webb Space Telescope, with its larger mirror and advanced infrared sensitivity, extended this reach even further. Early images from Webb show crowded star fields and diffuse clouds, glowing faintly in the mid-infrared, allowing astronomers to separate foreground structures from those at the true core. These observations confirm that the galactic center is a region of continuous star formation and decay, with intense radiation shaping the motion of gas and dust. Infrared spectroscopy, a technique that splits light into its component wavelengths, provided another breakthrough. By studying the spectra of stars orbiting near the center, astronomers determined their chemical compositions and motions along the line of sight. Some stars showed blue shifts moving toward us, others red shifts moving away. By combining these velocity measurements with their proper motions across the sky, the complete orbits could be reconstructed. This work, carried out over decades, became the foundation for the precise measurement of Sagittarius A star's mass. The power of infrared observation lies not only in what it reveals, but in how it connects phenomena across scales. It bridges the cool molecular clouds that block visible light and the hot ionized plasma near the core. It shows the life cycle of matter within the galaxy gas condensing into stars, stars shedding material, and that material drifting inward to feed the central black hole. The once opaque heart of the Milky Way becomes transparent through this method, allowing human vision extended by technology to reach regions once thought forever hidden. Through these observations, the story of the galaxy's center unfolds as one of gradual unveiling. Each wavelength adds a layer of comprehension. What began as a diffuse glow becomes a landscape of measurable detail. The dust, far from being an obstacle, acts as both a record and a participant in the processes shaping the core. Every photon that escapes from behind it carries information about temperature, density, and composition information that reconstructs the inner structure piece by piece. As this understanding deepens, attention turns toward the dense ring of molecular gas that surrounds the very center, the next region inward where conditions grow hotter, denser and more complex, marking the threshold of the central molecular zone. Within the innermost few hundred light-years of the Milky Way lies a region unlike any other in the galaxy, a dense and restless ring known as the central molecular zone. Here gas and dust reach concentrations thousands of times greater than those in the outer disk compressed by the combined gravity of the bulge and the inflow of material guided by the galactic bar. Temperatures fluctuate from the cold darkness of molecular clouds to the searing heat of ionized filaments that thread through the voids between them. This zone is not static. It is an ecosystem of motion and transformation, where the building blocks of stars and the ashes of past generations coexist in close proximity. The central molecular zone forms a rough torus or ring-shaped structure orbiting the galactic center at a distance of roughly 100 to 200 light-years. Its thickness varies, shaped by turbulence and magnetic pressure. Within it, massive clouds of molecular hydrogen dominate, each weighing millions of times the mass of the Sun. These clouds are bound by their own gravity but constantly stirred by shock stellar winds and the tidal forces that arise near the galactic nucleus. They twist and shear as they orbit, producing long filaments and streamers that connect the inner edge of the ring to the outer parts of the galaxy. These structures serve as conduits for gas flowing inward, feeding the dense core where Sagittarius A star resides. The conditions in this region are extreme even by galactic standards. Temperatures in dense clouds average around 100 degrees Kelvin, much warmer than the typical 10 degrees found in the outer molecular clouds. The density of particles can exceed 100,000 molecules per cubic centimeter, and the magnetic field strength is among the highest measured in the Milky Way. Infrared and radio observations reveal arc shells and elongated filaments crossing each other in intricate patterns. Some of these filaments trace magnetic field lines that extend vertically from the galactic plane, hinting at the presence of strong currents of charged particles moving through the medium. Within this environment, star formation proceeds vigorously but unevenly. In some locations, vast clusters of massive stars emerge from collapsing clouds, illuminating their surroundings with ultraviolet radiation. The Arches cluster and the quintuplet cluster are two of the most prominent examples, each containing thousands of stars packed within a few light years. Their winds and radiation carve cavities in the surrounding gas, producing expanding shells of ionized hydrogen. Elsewhere, other clouds remain dormant, their high turbulence preventing collapse. The balance between compression and disruption determines where and when stars will form, and in the central molecular zone this balance is constantly shifting. The chemical richness of this region is remarkable. Spectroscopic surveys detect complex organic molecules, formaldehyde, methanol, ammonia, and others mixed among the hydrogen and carbon monoxide that make up most of the mass. These compounds form on the surfaces of dust grains and are released into the gas when shocks or radiation heat the particles. Such chemistry provides clues about the physical conditions within the clouds and the processes that recycle material between generations of stars. The radiation fields here are intense, yet the dense gas provides protection for molecules to survive and evolve. Observations across different wavelengths reveal that the gas in the central molecular zone moves along eccentric orbits that bring it alternately closer to and farther from the galactic center. These oscillations create a pattern of compression, where clouds meet along their paths, igniting bursts of star formation. Numerical models suggest that these motions are guided by the gravitational potential of the galactic bar and the central mass concentration. The bar channels material inward until it reaches a radius where angular momentum and gravity reach temporary equilibrium. Their gas accumulates and forms the molecular ring seen in observations. Over time, some of this gas continues to lose energy and spiral closer to the center, eventually crossing into the immediate environment of Sagittarius A star. The energy balance of this region is delicate. Turbulent motions inject heat and support the clouds against gravitational collapse, while radiation and cooling allow them to condense. Supernova explosions from previous generations of massive stars further stir the gas-sending shock waves through the medium that compress or disperse nearby clouds. The result is a cycle of destruction and creation that maintains the molecular zone in a perpetual state of flux. From a distance it appears calm, but on closer inspection it is filled with expanding shells, colliding fronts and streaming filaments that evolve over tens of thousands of years. Magnetic fields play a critical role in shaping this environment. Polarized radio emission reveals long thread-like structures aligned perpendicular to the galactic plane. These magnetic filaments extend for dozens of light years and appear to connect the dense clouds to the hotter, more diffuse medium above and below the plane. The origin of these filaments remains under study, but they likely result from interactions between rotating gas and large-scale magnetic forces anchored in the central region. The alignment of these structures indicates that magnetism channels the movement of charged particles, influences cloud dynamics, and helps regulate the rate of star formation. Embedded within the molecular ring are regions of particularly high luminosity, where young massive stars heat their surroundings to thousands of degrees. These H2 regions, zones of ionized hydrogen, mark places where ultraviolet light from newborn stars strips electrons from atoms in the gas. The resulting plasma glows in infrared and radio wavelengths, outlining cavities carved by radiation pressure and stellar winds. Over time, these cavities expand, merge, and shape the structure of the entire ring. In some cases, they form bridges of material linking the inner edge of the zone to the nucleus, creating pathways through which matter can move inward. One of the most striking features seen in this region is the so-called radio arc, a complex of bright linear structures located a few dozen light-years from Sagittarius A star. It consists of parallel filaments emitting synchrotron radiation, produced by high-energy electrons spiraling around magnetic field lines. The radio arc intersects thermal filaments associated with the molecular zone, suggesting interaction between magnetic and ionized components. The coexistence of these different physical regimes, cold molecular gas, hot plasma, and relativistic particles, illustrates the diversity of processes at work near the galactic center. The central molecular zone also contains evidence of past energetic events. Observations of high-energy X-rays and gamma rays indicate that the region has experienced bursts of activity within the last few million years, possibly linked to flaring episodes of Sagittarius A star or collective supernova explosions. These events may have driven material outward in bipolar outflows, shaping the large-scale Fermi bubbles observed extending far above and below the galactic plane. Though their origins remain debated, such features demonstrate the deep connection between the molecular zone and the larger galactic environment. Despite its complexity, the overall structure of the central molecular zone acts as a reservoir of material for the black hole. Gas gradually loses angular momentum through collisions, magnetic interactions, and turbulence, allowing small amounts to drift inward. Most of this material forms the warm ionized structures that will later become part of the accretion flow around Sagittarius A star. The zone in this way represents the transition between the stellar environment of the bulge and the extreme gravitational regime of the galactic nucleus. As the perspective moves inward, the vast structures of the molecular zone begin to contract into a smaller and denser arena. The brightness intensifies, temperatures rise, and the distinction between individual clouds and the ambient medium blurs. The stars grow more numerous, their light mingling into a continuous glow. Gravity dominates over turbulence, drawing everything toward the hidden focus at the core. The next region ahead marks the boundary where the stellar density reaches its peak, the nuclear star cluster, the crowded gravitational heart that surrounds Sagittarius, a star itself. As the line of sight penetrates deeper into the inner galaxy, the ordered rotation of the Milky Way gives way to a realm of chaotic motion. Within the central molecular zone, gravity-magnetic fields and turbulent gas compete in a constant interplay of compression and release. The environment near the core cannot be described as calm or uniform. It is a restless atmosphere of shock waves, swirling eddies and streaming filaments. Every cubic light-year is alive with motion, from the slow drift of molecular clouds to the rapid vibration of charged particles spiraling along magnetic lines. This turbulence is invisible to ordinary sight, but recorded in radio-infrared and X-ray data as fluctuations in brightness and velocity. Together, these observations reveal a complex web of energy that sustains the central region in a state of dynamic equilibrium. The gas here is far from evenly distributed. Molecular clouds range in size from small clumps a few light-years across to enormous complexes containing millions of solar masses of material. Between them lie lower-density cavities filled with hot plasma and magnetic fields. The boundaries between these regions are not stable, but constantly shifting as energy flows across them. Shock fronts form where faster gas streams collide, compressing the material and raising temperatures to thousands of degrees. These shocks can trigger new star formation or disrupt existing clouds depending on their strength. The cycle of formation and destruction operates continuously, feeding energy into the surrounding medium and preventing it from collapsing completely under its own gravity. Magnetic fields thread through this chaos, invisible yet measurable, through their effects on light and charged particles. Radio observations reveal elongated filaments extending vertically across the galactic plane, each tracing a line of magnetic tension. These structures can stretch for tens of light years, appearing almost perfectly straight despite the turbulent environment around them. The stability of these filaments suggests that the magnetic field in the central region is remarkably strong, on the order of milligauss, hundreds of times stronger than the average field in the solar neighborhood. Such strength allows the field to influence the motion of gas and charged particles, shaping the geometry of the entire zone. The vertical orientation of many magnetic filaments indicates that the field may be anchored in the central region and extend outward above and below the plane. This configuration could channel energetic particles away from the core, forming part of the larger structures seen on galactic scales such as the Fermi bubbles that rise tens of thousands of light-years into the halo. Closer to the center, the magnetic field interacts directly with molecular clouds wrapping around them and guiding the flow of ionized gas along their surfaces. Observations show that some filaments appear to connect the dense molecular zone, with the hotter, more diffuse plasma outside acting as conduits for the transfer of energy and matter between phases of the interstellar medium. Inside this magnetic labyrinth, pressure and motion reach extraordinary levels. The gas exhibits velocity dispersions of more than 100 kilometers per second, meaning that different parts of a single cloud can move rapidly relative to one another. These internal motions broaden the spectral lines of molecules such as carbon monoxide and ammonia, allowing astronomers to measure the degree of turbulence. The data indicate that the turbulence is not random, but driven by organized processes, supernova explosions, stellar winds, and the gravitational tides from the dense stellar cluster at the center. Each of these injects kinetic energy into the gas, maintaining the restless character of the region. The central few hundred light-years also emits strong non-thermal radiation, the hallmark of relativistic particles accelerated by magnetic processes. Synchrotron emission arises when high-energy electrons spiral around magnetic field lines, releasing light across a broad range of wavelengths. This radiation outlines the filaments seen in radio images and provides clues to the interaction between magnetism and particle acceleration. In some locations, the filaments cross or twist around each other, forming junctions that may act as sites of enhanced activity where magnetic reconnection releases bursts of energy. These local events contribute to the background of X-ray and radio flares detected from the central region. Observations from X-ray telescopes such as Chandra and XMM Newton reveal hot plasma filling much of the space between the dense clouds. Temperatures of several million degrees indicate that this gas cannot be gravitationally bound and must eventually escape, yet continuous heating from stellar activity replenishes it. The plasma emits X-rays as electrons collide with ions, while the cooler, denser clouds emit radio and infrared radiation. The coexistence of such different temperatures within the same volume demonstrates how energy circulates through the system in complex ways. The balance between heating and cooling, compression and expansion keeps the region in a self-sustaining turbulent state. The relationship between magnetic fields and gravity becomes increasingly evident closer to the nucleus. Where gravity seeks to draw material inward, magnetic pressure can resist collapse, forcing gas to move along specific directions rather than falling freely. This interplay influences how material flows towards Sagittarius A star. In some regions, magnetic tension channels gas into narrow streams that spiral inward. In others, it prevents further infall by redirecting motion along field lines. The result is a patchwork of inflowing and outflowing zones that together regulate the rate at which matter approaches the central black hole. The same forces that shape the gas also affect the stars embedded within it. Massive clusters within the molecular zone move through the magnetic field, their stellar winds compressing nearby clouds and amplifying local turbulence. Supernova remnants expand asymmetrically under the influence of the field, producing elongated shells that align with magnetic directions. Over time, these feedback processes drive the large-scale circulation of material mixing hot plasma and cool gas into a constantly evolving mosaic. The region is also marked by periodic flashes of higher energy. Occasionally, the magnetic field reconnects lines of force break and rejoin, releasing stored energy in the form of particle acceleration and localized heating. These reconnection events may be responsible for some of the transient X-ray flares observed in the vicinity of the galactic center. While the largest of these outbursts originate from the immediate neighborhood of Sagittarius, a star, smaller ones occur throughout the surrounding area, contributing to the variable background that defines the central environment. Though invisible to the human eye, this turbulence leaves measurable fingerprints on the radiation that escapes. Polarization studies show that the magnetic field maintains a degree of order even amid the chaos, aligning dust grains and producing distinctive patterns in the emitted light. These observations help map the direction and strength of the field across the central region, revealing that it weaves through the molecular zone like an unseen scaffold holding the structure together. Without this magnetic framework, much of the gas might collapse into stars too quickly, or fall directly into the core, disrupting the delicate equilibrium of the galaxy's nucleus. From a larger perspective, the hidden turbulence and magnetic threads serve as the connective tissue between the molecular ring and the inner nucleus. They mediate the transfer of angular momentum, enabling some material to drift inward while holding the rest in place. They transform gravitational energy into heat and radiation, maintaining a balance that has persisted for millions of years. As the viewpoint moves inward from this zone of tangled forces, the scene begins to change again. The diffuse filaments thin and the density of stars increases sharply. The magnetic lines, once extended and open, start to twist and fold within a region of overwhelming gravitational influence. This is the beginning of the nuclear star cluster, where light motion and gravity converge around the unseen center that anchors the Milky Way. Moving inward from the magnetic labyrinth of the central molecular zone, the galaxy structure begins to tighten. The vast loops of gas and dust that filled the previous region narrow into streams and arcs. Temperatures climb as radiation from densely packed stars saturates the surrounding space. Gravity now dominates every motion. The transition from the molecular ring to the nucleus marks a change in both scale and energy. Distances shorten. Densities rise and the influence of the central mass becomes unmistakable. What once seemed like a crowded star field now resolves into a luminous swarm, where the distance between individual stars can be measured in thousandths of a light year. The inner few light years of the Milky Way are an environment without parallel, where the combined brightness of millions of stars merges into a nearly continuous glow surrounding the galactic center. The material entering this region has passed through multiple transformations. Clouds that began as diffuse hydrogen in the outer disk have condensed, fragmented, and been shaped by magnetic fields before reaching this depth. The result is a mix of molecular remnants, hot plasma, and stellar winds colliding within a narrow gravitational funnel. Gas temperatures rise to thousands of degrees, and shock fronts form where streams converge. As angular momentum carries some of the material around the core, the flow takes on a flattened disc-like shape. This structure feeds the inner environment, gradually delivering mass toward the domain dominated by the central black hole. The density of stars here is extraordinary. In a volume of space that would contain only a few stars in the solar neighborhood, millions are found orbiting the galactic nucleus. The light they produce saturates infrared images, creating a bright, concentrated sphere known as the nuclear stellar cluster. Many of these stars are old red giants, remnants of earlier generations born when the galaxy itself was younger. Others are surprisingly young, less than 10 million years old, indicating that star formation continues even under such extreme conditions. Their presence poses questions about how stars can form in a place where tidal forces from the central mass should tear clouds apart before they can collapse. Yet somehow pockets of gas manage to resist disruption long enough for new stars to emerge. Observations show that these stars move at remarkable speeds. Those closest to the center travel at thousands of kilometers per second, completing entire orbits in just a few decades. Their paths are not random, but follow precise ellipses around a single unseen point. This motion provides one of the clearest pieces of evidence for the enormous gravitational influence exerted by Sagittarius A star. The total mass required to produce such orbits, roughly 4 million times that of the Sun, cannot be accounted for by the visible stars alone. The concentration of this mass within a region smaller than our solar system indicates that only a supermassive black hole can explain the observations. As these stars sweep around the center, their radiation interacts with the surrounding gas, producing a complex interplay of heating and cooling. The winds from massive stars collide and generate shock waves that compress nearby clouds, forming localized regions of high pressure. These interactions produce diffuse X-ray and infrared emission, creating a luminous fog that fills the inner parsec. Each collision, each flash of energy contributes to the background glow detected by telescopes observing the galactic core. The environment is so energetic that even though much of the material is too diffuse to emit visible light, it glows brightly in infrared and radio frequencies. Embedded within this crowded field are structures of gas orbiting in rings and streams. One of the most notable is the circumnuclear disk, a torus of molecular material rotating around the center at a distance of a few light years. It acts as a transitional zone between the dense stellar cluster and the immediate surroundings of Sagittarius A star. The disk's rotation is irregular, influenced by both the gravity of the black hole and the collective mass of the stars. Observations show clumps of gas moving at hundreds of kilometers per second, producing broad spectral lines that testify to the region's extreme dynamics. Inside this radius, the gas becomes ionized and forms a hot, thin plasma known as the mini-spiral. The mini-spiral consists of several distinct arms of ionized gas curving toward the center. These filaments appear in infrared and radio images as glowing threads winding inward like streams converging toward a drain. They are channels through which material flows towards Sagittarius A star, though much of it never reaches the event horizon. Stellar winds and radiation pressure from nearby stars deflect or evaporate much of the gas before it can fall inward. The remaining fraction continues to spiral closer, gradually heating as it encounters stronger gravitational and magnetic forces. Within the nuclear cluster, the interaction between stars adds further complexity. Close encounters are frequent compared to ordinary galactic environments. Some stars may be ejected entirely from the region, slingshotted by gravitational interactions into the outer galaxy as hypervelocity stars. Others merge or are tidally stripped by the black hole if they venture too near. The balance of creation and destruction defines this inner domain. It is a laboratory of extreme astrophysics, where the laws of motion and gravity can be observed operating at their most intense, yet most precise scales. The infrared observations from the Keck Observatory and the Very Large Telescope have captured these motions with stunning accuracy. By tracking individual stars year after year, astronomers have drawn detailed maps of their orbits. The star known as S2 is among the most studied. It completes its orbit around Sagittarius A star in about 16 years, approaching as close as 17 light hours at its nearest passage. At that distance, it moves at more than 7,000 kilometers per second, fast enough to circle the Earth in less than a minute. Measurements of its motion confirm the predictions of general relativity. The path of the star's light bends under the intense gravitational field, and its clock appears to slow relative to observers farther away. Such precision allows the mass of the central object to be measured with remarkable confidence. The gravitational potential of this region shapes not only the stars but also the distribution of dark matter and stellar remnants. Black holes and neutron stars, remnants of previous generations, drift through the nuclear cluster. Their interactions may produce X-ray binary systems, where one star feeds gas onto a compact companion. These contribute to the flickering high-energy background that characterizes the galactic center. Every few decades, one of these systems brightens as it enters a phase of rapid accretion, before fading again into obscurity. The inward journey also reveals variations in chemical composition. The gas within the nuclear cluster shows enhanced levels of heavy elements compared to the outer galaxy, a sign of repeated cycles of star formation and supernova enrichment. These elements, carbon, oxygen, silicon, and iron, provide the opacity that cools clouds and allows new stars to form despite the harsh environment. Radiation from the massive stars ionizes much of the gas, while dust grains scatter and absorb the light, creating diffuse halos of emission. Observing these effects allows scientists to reconstruct the density and temperature profiles within the cluster, offering insight into how matter behaves near a supermassive black hole. The energy radiated by this region fluctuates over time. Infrared and X-ray telescopes detect frequent flares that rise and fade within hours, indicating sudden bursts of activity near the black hole. Some originate from colliding winds or magnetic reconnection events. Others may be caused by small clouds or asteroids drawn too close and heated as they disintegrate. These flares serve as reminders that even in its relative quietness, Sagittarius A exerts continuous influence on its surroundings. The closer the gaze moves toward the nucleus, the more the scale compresses. Structures that once spanned hundreds of light years shrink to just a few. The interplay of light and gravity becomes more pronounced, and the motions of stars trace invisible curves that all converge on the same point. Beyond this threshold lies the domain of the S-stars, a handful of young, massive objects whose precise orbits have revealed the true nature of the galactic center. As the view narrows to their region, the story turns from the crowded brilliance of the cluster to the isolated dance of stars moving at relativistic speed around a single unseen focus. At the very heart of the Milky Way lies the nuclear star cluster, a brilliant and compact sphere of light that surrounds the unseen black hole. It spans only a few light years, yet contains millions of stars packed so tightly that their combined glow merges into a soft radiance when viewed through infrared telescopes. The airless void of space here is saturated with radiation. Every cubic region of space is filled with overlapping stellar winds, magnetic fields, and streams of plasma. Gravity dictates the movement of everything from the smallest dust grains to the most massive suns, binding this swarm into an intricate balanced system that orbits the invisible center known as Sagittarius A. The cluster's structure is layered. The outer regions blend gradually into the central molecular zone, but as one moves inward, the concentration of stars rises sharply. Within a single light year, stellar density exceeds 1,000,000 times that found near the Sun. Most of these are old stars, faded red giants, and compact remnants that have survived countless orbits around the center. Yet among them exists a population of hot young stars, some only a few million years old. Their presence is unexpected in such a turbulent, gravitationally hostile environment. The tidal forces from the black hole should tear apart any cloud of gas before it can collapse into stars, yet these luminous youths endure, suggesting that star formation here follows mechanisms unlike those in the galaxy's calmer outskirts. Observations show that many of the young stars are arranged in disks or streams, rather than random orbits, indicating that they may have formed in situ from dense gas accreted into the nucleus. One possibility is that massive molecular clouds from the central molecular zone were drawn inward, compressed by tidal forces, and fragmented into smaller pieces that quickly formed stars before being dispersed. Another possibility is that stellar clusters formed farther out migrated toward the center. Through gravitational interactions, their outer layers stripped away, while their cores survived to populate the inner region. Either path reflects the intense dynamism that governs the cluster's evolution. The environment within the cluster is defined by extremes. Temperatures of the gas can reach several thousand degrees, while radiation pressure from the massive stars sculpts the surrounding dust into arcs and filaments. Stellar winds collide at supersonic speeds, creating shock waves that produce diffuse X-ray emission. Each massive star releases energy equivalent to millions of suns, and their combined influence generates a luminous fog of ionized gas that fills the cluster's interior. This glow, visible in infrared and radio wavelengths, outlines the gravitational boundaries of the system. Beyond it, the light begins to thin, and the environment transitions into the domain of the circumnuclear disk and the black hole's immediate surroundings. The motions of the stars within the cluster are the key to understanding the mass distribution of the central region. Each star moves on an orbit determined by the total gravitational field, and by tracking these orbits over time, astronomers can reconstruct the invisible landscape that governs them. The stars nearest to Sagittarius A, display the most dramatic behavior. Their trajectories bend sharply around an unseen focus, and their velocities reach thousands of kilometers per second. These observations provide direct evidence for the presence of a supermassive black hole. Without such a compact and massive object, the orbits would be impossible to sustain. The star known as S2 provides the clearest example of this phenomenon. Over the course of 16 years, it traces an elongated ellipse around the galactic center, approaching to within a few dozen times the distance between the Earth and the Sun at its closest point. When it reaches this periapsis, its speed peaks near 3% of the speed of light. The gravitational field it experiences is so strong that measurable relativistic effects appear. Its light is redshifted as it climbs out of the potential well, and its orbital path precesses slightly with each revolution precisely as predicted by general relativity. Decades of careful observation from instruments such as the Keck Observatory and the Very Large Telescope have confirmed these details, allowing astronomers to measure the mass of Sagittarius A with unprecedented accuracy. Other stars, collectively known as the S-stars, follow similarly tight orbits, each providing an additional data point that refines the model of the gravitational potential. Their variety of paths, some nearly circular, others highly elongated, reveals how chaotic the region can be. Collisions, close encounters, and gravitational interactions constantly reshape the distribution of angular momentum. Occasionally a star strays too close to the black hole and is torn apart by tidal forces, producing a brief flare of radiation as its material spirals inward before disappearing beyond the event horizon. Such events are rare on human timescales, but inevitable in the long life of the cluster. The nuclear star cluster also contains a hidden population of compact remnants, neutron stars, white dwarfs, and smaller black holes left behind by previous generations. These invisible members interact gravitationally with the luminous ones, subtly altering their motions. Some of these remnants form binary systems that emit bursts of X-rays as matter transfers from one partner to the other. Others may merge or be captured by the central black hole, adding to its mass over cosmic time. The density of such remnants is thought to increase sharply toward the center, creating a cusp of dark matter and stellar debris that contributes to the gravitational field. The radiation environment within the cluster is intense. Ultraviolet light from massive stars ionizes the gas, while their winds fill the volume with high-speed particles. Yet despite these harsh conditions, dust persists, surviving in the shadowed regions between stars. This dust absorbs the ultraviolet light and irradiates it in the infrared, giving the cluster its distinctive glow when observed through telescopes sensitive to long wavelengths. The balance between destruction and replenishment keeps the dust population stable, ensuring that each new generation of stars forms within an environment enriched by the remnants of its predecessors. The energy released within the cluster does not escape easily. The gravitational potential traps much of it, allowing the core to maintain a steady temperature over long time scales. Occasional supernovae inject bursts of kinetic energy, stirring the gas and briefly disturbing the equilibrium. The shock waves from these explosions propagate through the cluster, compressing some regions while clearing others, setting the stage for future cycles of star formation. Over millions of years, these processes create the layered structure observed today, a core dominated by young hot stars surrounded by shells of older populations fading into the larger bulge. Infrared and radio surveys map the cluster with remarkable precision. Adaptive optics correct for the blurring of Earth's atmosphere, revealing individual stars even in the densest regions. Each data point contributes to a long-term timeline showing how the system evolves. The star's positions, velocities, and spectral properties combine to form a three-dimensional model of the galactic center, confirming that the gravitational potential is dominated by a point-like mass, the supermassive black hole Sagittarius A star. The nuclear cluster therefore acts as both a veil and a probe. Its stars hide the black hole from direct optical view, but simultaneously trace its presence through their motion. As the narrative moves further inward, the density of material continues to rise, but the number of visible stars begins to thin. Radiation pressure and tidal forces clear a small cavity near the center, leaving an environment dominated not by stellar light, but by the hot plasma and magnetic fields surrounding the black hole. Here the cluster gives way to the accretion flow, where gas streams spiral at nearly the speed of light, generating energy that radiates outward across the electromagnetic spectrum. The journey that began in the calm spiral arms of the Milky Way now reaches the boundary where ordinary stellar dynamics transition into the physics of extreme gravity. Deeper within the nuclear star cluster, at the very edge of the gravitational abyss, a small group of stars performs a dance of astonishing precision. These are the S stars, a handful of bright and youthful suns moving at immense speeds around an invisible focus that marks the true location of Sagittarius A star. They trace elongated orbits that carry them alternately far from and perilously close to the black hole, their paths determined entirely by its gravitational pull. Each star serves as a natural probe of the extreme environment surrounding the center of the Milky Way, providing direct evidence for the existence and nature of the supermassive object hidden within. The star known as S2 has become the most studied of this group. Infrared telescopes have tracked it for more than 3 decades, capturing its position as it sweeps through space with extraordinary speed. At its farthest, S2 lies about 1/10 of a light-year from the center, but every 16 years it plunges inward to a distance of only 17 light-hours. At that moment it moves at nearly 8,000 kilometers per second, faster than any planet or star elsewhere in the galaxy. This motion carries it deep into the region where space-time itself is warped by gravity. The light from S2 shifts toward the red as it climbs out of the black hole's potential, a measurable signature of general relativity. Its orbit precisely mapped by the Keck Observatory and the Very Large Telescope confirms a central mass of about 4 million solar masses, confined within a volume smaller than the solar system. No collection of ordinary stars or stellar remnants could produce such a concentration. Only a supermassive black hole fits the evidence. S2 is not alone. More than 24 other S stars have been identified, each following its own intricate path. Their orbits vary widely, some nearly circular, others stretched into long ellipses that carry them far from the center before they curve back. Together they form a dynamic cluster bound by the black hole's immense gravity. Their speeds and directions change continuously as they move through a landscape of invisible forces. The closest among them, such as S62 and S46, approach the black hole to distances even smaller than S2's completing orbits in less than a decade. These swift motions unfold within volumes of space that light can cross in only a few hours, regions where gravitational effects dominate over all other influences. Observing these stars requires extraordinary precision. Infrared wavelengths are essential because dust blocks visible light from reaching Earth. Using adaptive optics and interferometric techniques, astronomers can resolve the cluster to accuracies measured in microarc seconds, equivalent to discerning a coin on the surface of the Moon. By combining measurements taken over many years, they reconstruct full 3-dimensional trajectories. These maps reveal how the stars accelerate as they near the center, slow as they recede, and precess over time due to relativistic corrections. Each orbit thus becomes both a test of gravity and a chronicle of the galactic center's history. The youth of the S stars remains a puzzle. Their spectra indicate ages of only a few million years, yet the tidal force is so close to Sagittarius, a star, should prevent any ordinary star formation. The gas clouds needed to create them would be torn apart before collapsing. Several explanations have been proposed. One possibility is that these stars formed farther out in the disk of the nuclear cluster and migrated inward through gravitational interactions, a process known as dynamical friction. Another suggests that they formed within a dense self-gravitating disk of gas orbiting the black hole, where the competing forces of rotation and gravity could balance just long enough for new stars to emerge. However they originated, they now serve as traces of the black hole's influence, their presence demonstrating that even in the most hostile conditions, the cycle of stellar birth and evolution continues. The black hole's tidal field shapes every aspect of their motion. As the stars approach pericenter, their closest point to the center, the gravitational gradient across each star becomes extreme. The difference in pull between the near and far sides could stretch and distort them, though their internal pressure prevents complete disruption. The light they emit varies slightly as they swing around the black hole, brightening when compressed by gravitational lensing and fading again as they move away. These subtle changes carry information about the curvature of spacetime itself. By analysing them, astronomers test the predictions of Einstein's theory at scales far beyond those available in any laboratory. The region inhabited by the S-stars is not empty. It is filled with tenuous plasma and magnetic fields left over from the winds of nearby massive stars. This medium interacts with the stars as they move, producing faint trails of ionized gas detectable in infrared and radio wavelengths. In some cases, these interactions may trigger short-lived flares of emission, as material is heated by compression or friction. The resulting glow contributes to the variable background radiation that characterizes the central parsec. Every flare, no matter how brief, offers another glimpse of the processes linking the visible stars to the invisible core. Occasionally, two stars pass close enough to alter each other's paths through gravitational encounters. Over long timescales, such interactions randomize the orbits, gradually erasing any initial pattern of motion. Some stars gain energy and are ejected from the cluster, entirely becoming hypervelocity stars that escape the galaxy's gravitational pull. Others lose energy and spiral inward, perhaps to be consumed by the black hole. This exchange of energy and momentum ensures that the region remains dynamically active, a small but enduring example of the continual reshaping that defines galactic evolution. The detailed monitoring of these stars has refined the measurement of Sagittarius, a star's position, to extraordinary accuracy. The center of all their orbits coincide within less than 1,000th of a light year, confirming that the mass resides in a single compact object. Moreover, the slight deviations from perfect Keplerian motion caused by relativistic effects and by the distributed mass of surrounding stars allow astronomers to infer the geometry of spacetime near the event horizon. Each completed orbit adds to this picture, gradually transforming abstract theory into observable reality. Beyond their scientific significance, the S-stars illustrate the scale of contrast at the galaxy's core. They are ordinary objects by cosmic standards, younger, luminous, and massive, but their setting magnifies every aspect of their existence. Their orbits, measured in decades rather than millennia, trace patterns of motion that would take place far too slowly to witness anywhere else. Here near the black hole, human observation spans enough time to record the full sweep of a stellar revolution. The precision of these measurements turns the galactic center into a natural observatory of gravity, where the curvature of space-time becomes visible through the motion of light and matter. The radiation from the S-stars also affects the material surrounding the black hole. Ultraviolet light and stellar winds strip electrons from nearby gas, maintaining a region of ionized plasma that serves as the outer boundary of the accretion flow. This interaction connects the stars directly to the feeding process of Sagittarius A star. Their energy heats and stirs the gas, influencing how much material eventually falls inward. The balance between these competing processes, heating from the stars and cooling from radiation, determines the faint level of activity that distinguishes Sagittarius A star from brighter, more violent black holes in distant galaxies. In the innermost part of this region, where only a few stars remain, the gravitational potential steepens sharply. Beyond this point, stable orbits become impossible for ordinary stars, and the domain of freely orbiting bodies gives way to that of swirling plasma and relativistic particles. The S stars mark the final frontier where light and matter still follow classical motion, before entering the regime of extreme gravity. From their positions, one can trace the transition between the stellar dynamics of the cluster and the accretion processes that operate just outside the event horizon. The observation of these swift stars has transformed understanding of the Milky Way's core. What was once an abstract hypothesis has become a directly measured reality. Their paths chart the invisible landscape of space-time around Sagittarius A star, mapping the boundary between the known and the unknowable. As the gaze moves still closer to the centre, the bright points of the S stars fade into the diffuse glow of heated gas. The stars that once traced the black hole's influence give way to the material that feeds it, a continuous flow of plasma, spiralling inward under the pull of gravity. In this next region, light itself begins to curve, and the language of motion shifts from orbits to accretion, where matter surrenders its energy before vanishing from view. At the centre of all motion, behind the glow of stars and the turbulence of gas, lies a point that emits almost no visible light. Its presence cannot be seen directly, yet its influence is undeniable. The stars of the nuclear cluster trace invisible paths around it, their orbits governed by its immense gravity. This object, Sagittarius A star, was first identified not through sight, but through its signature in radio waves. In the early 1970s, astronomers discovered that amid the complex emissions of the galactic centre, there existed a compact and unusually bright source, only a few light hours across. Over the decades that followed, successive generations of instruments refined this discovery, revealing that the object's position coincided exactly with the focal point of all stellar orbits. What could not be observed through light was measured through motion, a gravitational fingerprint pointing to a supermassive black hole at the heart of the Milky Way. The process of measuring such an invisible entity required patience and precision extending over decades. Infrared telescopes equipped with adaptive optics became the primary tools for this task, allowing astronomers to track individual stars with exquisite accuracy. Each star near the galactic centre follows an elliptical path that repeats over time, providing direct evidence of the gravitational potential. By plotting these paths in 3 dimensions, scientists could deduce both the mass and the size of the central object. The results converged consistently, a mass of roughly 4 million suns confined within a sphere smaller than the orbit of Mercury. No known configuration of star's gas or dark matter could remain stable under such density. The only plausible explanation was a black hole. The most direct measurements came from the motion of the star S2, which completed its orbit in 16 years. When it reached its closest approach to Sagittarius A star in 2018, it passed through a region where relativistic effects became measurable. The gravitational redshift of its light, the stretching of its wavelengths as it escaped the black hole's gravity, matched precisely the predictions of general relativity. The curvature of its orbit also revealed a slight precession, the slow rotation of its ellipse in space another hallmark of Einstein's theory. Together, these observations provided the most compelling proof yet that the central object obeys the physics of a black hole, where matter and energy are confined by space-time curvature itself. Measuring motion on such scales demanded not only clear skies but global collaboration. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and a network of radio arrays across Earth worked in concert to observe the galactic center at multiple wavelengths. Radio interferometry allowed baselines thousands of kilometers wide, giving the resolving power equivalent to a telescope the size of the planet. This technique, known as very long baseline interferometry, was crucial to narrowing down the true extent of Sagittarius A. By correlating signals recorded at different locations, astronomers synthesized an image of extraordinary detail, capable of distinguishing features as small as the orbit of Mercury from a distance of 26,000 light-years. Early results from this work revealed that Sagittarius A is remarkably quiet. Unlike the luminous quasars seen in distant galaxies, it emits only a faint trickle of radiation. Its energy output is millions of times weaker than that of active galactic nuclei of comparable mass. This low luminosity puzzled astronomers. If the black hole's gravity is so immense, why does it not produce the same blazing jets and accretion disks seen elsewhere? The answer lies in its environment. The amount of material available for accretion is small, and much of it is hot and diffuse, unable to radiate efficiently. Instead of forming a bright disk, the gas around Sagittarius A swirls in a thick turbulent flow, known as a radiatively inefficient accretion flow. In this regime, most of the gravitational energy gained by falling material is carried inward rather than radiated away, leaving the system dim despite its power. Radio and X-ray observations support this model. The gas surrounding the black hole glows faintly in these wavelengths, revealing temperatures of millions of degrees, but densities far below those in more active systems. The plasma moves at relativistic speeds but radiates little energy. Occasionally a small fluctuation in the magnetic field or a clump of material falling inward produces a brief flare, a sudden brightening that lasts for hours before fading again into quiescence. Such events confirm that Sagittarius A is not entirely dormant, but experiences intermittent bursts of activity as it consumes tiny amounts of matter from its surroundings. Measuring these fluctuations requires constant vigilance. Instruments like NASA's Chandra X-ray Observatory and the Very Large Array have monitored the galactic center for years, recording variations in brightness and spectrum. These data reveal that Sagittarius A produces several flares each day, though most are weak and short-lived. The most intense events emit X-rays hundreds of times brighter than the baseline level corresponding to rapid heating of gas near the event horizon. The cause is likely magnetic reconnection, the sudden reconfiguration of magnetic field lines that releases stored energy similar to solar flares on the Sun but vastly more powerful. These phenomena provide rare glimpses into the processes operating just outside the black hole's boundary. Precision timing of the flares combined with measurements of the orbits of nearby stars allows astronomers to refine the physical parameters of the system even further. The mass spin and orientation of Sagittarius A are gradually becoming measurable quantities rather than abstract estimates. Data suggest that the black hole rotates, though more slowly than many of its counterparts in active galaxies. Its spin axis appears roughly aligned with the rotation of the surrounding gas, consistent with a long evolutionary history shaped by the steady accretion of material from the Milky Way itself, rather than by major collisions. Measuring the invisible giant also extends beyond direct observation. theoretical modeling plays a crucial role. Supercomputer simulations replicate the physics of magnetized plasma, swirling in curved space-time, predicting how such flows should emit radiation at different wavelengths. These models are compared with actual data to test assumptions about temperature density and magnetic strength. When simulations reproduce the observed light curves and spectral shapes, confidence grows that the underlying physics is correct. In this way, observation and theory converge, each refining the other, until the invisible becomes quantifiable. The culmination of this effort arrived with the Event Horizon Telescope, a global network of radio observatories synchronized to act as a single Earth-sized instrument. In 2022, after years of data collection and calibration, this collaboration released the first image of Sagittarius A star. The image did not show the black hole itself, which by definition emits no light, but rather the ring of emission produced by photons orbiting near the event horizon. The circular glow surrounding a central shadow matched the predictions of general relativity almost perfectly. For the first time, humanity could see the outline of the gravitational well that holds the galaxy together. The measurement confirmed that the mass and size derived from decades of stellar orbit observations were accurate, uniting visual evidence with dynamical proof. Though the image appeared faint and blurry compared to artistic expectations, its significance was immense. It provided the most direct confirmation yet that the Milky Way harbors a supermassive black hole, validating decades of theoretical work and observational persistence. The brightness asymmetry around the ring indicated the direction of rotation, revealing how space-time bends and amplifies light from the swirling plasma. Every photon captured in that image had traveled 26,000 years to reach Earth, carrying with it the final echoes of matter as it circled the threshold of no return. With these measurements, Sagittarius A star ceased to be a mere inference. It became a defined object with mass, spin and structure and astronomical reality rather than an idea. Yet despite this precision, mystery remains. The same data that confirmed its existence also highlighted its silence. The black hole consumes matter, inefficiently, radiates weakly, and exerts its influence with quiet persistence. In contrast to the violent cores of distant quasars, the center of our galaxy endures in a state of subdued equilibrium, neither dormant nor explosive, but steady and enduring. This quietness, far from diminishing its significance, makes it an ideal laboratory for studying gravity itself. As the view continues inward beyond the stars and orbits that revealed its presence, the focus shifts from measurement to the environment immediately surrounding Sagittarius A star. Here, the black hole's accretion flow dominates a faint whirlpool of hot plasma, shaped by magnetic fields and curved space-time. The dynamics of this inner region will illuminate how even a nearly silent black hole continues to influence everything around it. The supermassive black hole at the heart of the Milky Way does not roar with the brilliance of an active quasar. Instead, it feeds in near silence. Sagittarius. A star exerts an immense gravitational pull, yet its surrounding environment offers little to consume. The gas that drifts inward from the central molecular zone is thin, hot and turbulent, lacking the density to radiate strongly, or to form the brilliant accretion disks seen around more energetic black holes. As a result, our galaxy's central giant glows faintly, producing a steady murmur of radio and infrared light rather than a blazing beacon. This subdued state defines the Milky Way's nucleus, a regime of slow accretion, where matter falls inward but releases only a fraction of its potential energy. The journey of this gas begins far from the event horizon. Streams of material pulled from the central molecular zone enter the nuclear region, and lose angular momentum as they interact with magnetic fields and stellar winds. Only a small portion manages to spiral closer, crossing the boundary of the circumnuclear disk and joining the tenuous plasma that orbits near the black hole. Most of it remains suspended in looping orbits deflected by magnetic pressure or expelled by radiation from nearby massive stars. The amount of matter actually reaching the black hole each year is tiny, comparable to the mass of a small asteroid, yet it is enough to maintain a faint but measurable glow across radio and X-ray wavelengths. This type of accretion flow, known as a radiatively inefficient accretion flow, behaves differently from the thin, bright disks found in active galaxies. In those systems, gas cools efficiently, settling into a flat, dense structure that converts gravitational energy into light with high efficiency. Around Sagittarius, a star, however, the gas remains too hot to condense. Temperatures soar to tens of millions of degrees, and the particles move so rapidly that they cannot easily transfer energy or lose it through radiation. Instead, most of the heat is carried inward with the gas and swallowed by the black hole. This process produces only a weak glow, most prominent in radio and submillimeter wavelengths. The energy output of Sagittarius A star is less than 1/billionth that of an average quasar, despite its enormous mass. Within this dim regime, the flow of matter becomes turbulent and complex. Magnetic fields thread through the plasma, twisting and reconnecting as charged particles spiral along them. The energy released in these magnetic interactions powers brief flares, flashes of light that punctuate the otherwise steady emission. These outbursts are recorded by telescopes like Chandra and the Very Large Array, revealing that Sagittarius A star flickers several times per day, each event lasting from minutes to hours. The brightness can increase by factors of hundreds during these episodes, then fade again into quietness. Such flares may occur when small clumps of material orbits too close to the black hole and are rapidly heated by friction and magnetic reconnection before being consumed. Despite its faintness, Sagittarius A star emits across a wide spectrum. In radio wavelengths, it appears as a compact but extended source, corresponding to the region where the plasma becomes opaque to its own emission. At shorter wavelengths in the submillimeter and infrared, the emission originates closer to the event horizon. X-rays arise from the hottest and most energetic particles near the inner edge of the flow. Together, these observations allow astronomers to construct a multi-wavelength portrait of the black hole's feeding behavior. Each wavelength reveals a different layer of the surrounding environment, from the outermost turbulent plasma to the innermost region where gravity bends light. The flow of gas around Sagittarius A star does not form a uniform structure. It resembles a thick, slowly rotating sphere rather than a thin disk. The outer regions are dominated by turbulent eddies and magnetic loops, while the inner regions flatten slightly as centrifugal forces increase. Simulations show that some of the gas, rather than falling inward, is expelled in weak outflows. These winds carry away angular momentum and energy, reducing the amount of matter that can reach the event horizon. The result is a self-regulating system. The black hole's own faint activity limits how much it can feed, maintaining the balance that keeps it quiet. The contrast between Sagittarius A star and the luminous black holes at the centers of active galaxies offers insight into galactic evolution. The Milky Way may once have passed through a more energetic phase when greater supplies of gas flowed into the center. Evidence for this comes from giant structures called the Fermi bubbles, vast lobes of gamma-ray emission, extending tens of thousands of light-years above and below the galactic plane. These bubbles suggest that several million years ago, the black hole released powerful jets, or winds that inflated them. Since then, the fuel supply has diminished, leaving the nucleus in its current subdued state. The present quietness may therefore represent a temporary pause in a much longer cycle of feeding and dormancy. Even in this calm phase, the environment close to Sagittarius A star remains dynamic. Gas clouds occasionally venture too near, drawn by the black hole's gravity. In 2013, astronomers observed one such cloud known as G2 on a trajectory that would bring it dangerously close to the event horizon. Prediction suggested that it might be torn apart and ignite a bright flare. As the cloud reached pericenter, however, it survived with little disruption, indicating that it contained a dense core, perhaps even an embedded star. The event demonstrated how complex and unpredictable the interactions near Sagittarius A star can be. Small differences in composition density or magnetic structure can determine whether a body is destroyed or merely deflected. The surrounding population of stars continues to influence the flow of material as well. Stellar winds from hot, massive stars inject gas into the region, providing a slow but steady supply of potential fuel. Some of this gas is ionized and joins the diffuse plasma. Some is heated by collisions and carried outward again. The result is a continuous circulation that maintains a delicate balance between inflow and outflow. The energy output from Sagittarius A star, though low by cosmic standards, is sufficient to stabilize this equilibrium, preventing excessive buildup of matter that could reignite a more active phase. The faintness of the black hole has also been a scientific advantage. Its low brightness allows astronomers to study its environment without the glare that obscures similar regions in distant galaxies. Through Sagittarius A star, the physics of accretion can be explored in unprecedented detail. Observations across decades have revealed subtle patterns in its variability, suggesting that even within the apparent calm turbulence, and magnetic processes operate continuously. Supercomputer simulations reproduce this behavior, showing how eddies of plasma twist and merge as they approach the event horizon, each releasing a brief flash before disappearing. The spectral signature of Sagittarius A star carries the imprint of these processes. At radio frequencies, its emission follows a characteristic curve that rises toward the sub-millimeter band and then declines. This shape indicates that synchrotron radiation from relativistic electrons dominates with only minimal contribution from thermal emission. At higher energies in the X-ray range, the spectrum reveals non-thermal tails consistent with particles accelerated in magnetic reconnection events. Every feature of this faint light encodes the story of matter surrendering its energy to gravity. The quiet hunger of the black hole has lasted for millions of years, but it may not remain so forever. If a dense cloud or a disrupted star were to fall inward, Sagittarius A star could flare to luminosities rivaling quasars, transforming the center of the Milky Way into a radiant source visible across the cosmos. For now, however, the giant rests, consuming just enough to reveal its presence, while remaining largely invisible. It anchors the galaxy with its gravity, shaping the motion of stars and gas without announcing itself through light. Beyond this stillness lies a more extreme zone where the plasma itself approaches the speed of light, and the effects of general relativity dominate every observation. Here, radiation bends, time dilates, and magnetic energy twists into luminous arcs. This is the inner accretion flow, the final stage before matter crosses the event horizon. The faint glow that surrounds Sagittarius. A star originates there from a region only a few times larger than the black hole itself. To understand how light emerges from this boundary, the view must move closer still to the swirling luminous plasma that defines the threshold between visibility and darkness. Within a few dozen times, the radius of the event horizon gravity begins to dominate absolutely. The gas that has survived the long journey inward now forms a hot tenuous plasma swirling around Sagittarius A star in a complex turbulent flow. This is not a smooth or uniform disk, but a chaotic whirlpool of ionized matter where magnetic fields, relativistic motion and radiation all interact. Temperatures in this region reach tens of millions of degrees, and particles move at speeds approaching that of light. The plasma glows faintly in radio-infrared and X-ray wavelengths, releasing the last energy it possesses before crossing the point of no return. Here the concept of orbit starts to dissolve. Motion becomes dictated by space-time itself, curved into tight spirals that lead inevitably inward. The plasma consists primarily of electrons and protons stripped from hydrogen atoms by intense heat. At such temperatures, collisions between particles occur frequently enough to maintain a shared energy, but not often enough to produce efficient radiation. This is why the region remains dim despite its high temperature. The energy generated by gravitational compression is carried inward rather than radiated outward. The result is a low luminosity accretion flow, a state in which most of the matter simply vanishes without fanfare, swallowed whole by the black hole. Computer models suggest that the density of gas near the event horizon is only a few hundred particles per cubic centimetre, far emptier than any vacuum achievable on Earth. Yet this near emptiness glows faintly, a last whisper of light from matter on the verge of disappearance. The magnetic fields in this plasma play a crucial role. Twisted by differential rotation, they form loops and arcs that rise from the flow like luminous threads. When these field lines reconnect, snapping and merging, they release bursts of energy that heat nearby particles and produce the short-lived flares observed by telescopes. These magnetic events may also generate brief outflows, ejecting small amounts of matter before it can fall inward. The process is chaotic but continuous, maintaining a delicate balance between inflow and ejection. Every flare represents a localized restructuring of the magnetic field, a momentary release of tension in an otherwise restrained environment. The plasma's behavior is governed by relativity. Close to the event horizon, the curvature of spacetime warps the paths of particles and light alike. The inner regions rotate faster than the outer ones, creating strong shear that amplifies magnetic fields and drives turbulence. This combination of gravitational and magnetic forces shapes the geometry of the flow into a roughly toroidal structure, flattened but thick. The motion is nearly Keplerian, meaning that orbital speed decreases with distance, but relativistic corrections alter this pattern. At a certain radius known as the innermost stable circular orbit, matter can no longer maintain a steady path. Beyond that point, it plunges inward at near light speed, releasing the last of its energy as it crosses the event horizon. Observing this region directly requires extraordinary resolution. The Event Horizon Telescope provides the clearest view, revealing a faint ring of emission surrounding a dark center. This ring corresponds to light bent by gravity into a circular path around the black hole. The brightness varies around its circumference, enhanced on one side by Doppler, boosting as material moving toward the observer appears brighter. This asymmetry confirms the rotation of the plasma and indirectly the spin of the black hole itself. The structure of the ring agrees remarkably well with predictions derived from Einstein's equations, providing visual confirmation that space-time behaves as theory describes even under the most extreme conditions. The plasma's motion is not purely inward. Simulations and polarization measurements suggest that small-scale winds and jets occasionally form carrying energy outward. These outflows are weak compared to those of active galactic nuclei, but still influence the surrounding environment. They help regulate the inflow of new material, ensuring that Sagittarius A* remains in its current low luminosity state. The combination of inflow-outflow and magnetic activity forms a self-sustaining cycle. The black hole consumes matter, slowly heating and expelling just enough to prevent runaway accretion. This quiet equilibrium may persist for millions of years unless disturbed by an external influx of gas. The radiation produced by the hot plasma originates through synchrotron emission, a process in which relativistic electrons spiral around magnetic field lines and emit light. This radiation spans from radio to X-ray wavelengths depending on particle energy and magnetic strength. At lower frequencies, the emission is absorbed by the plasma itself, creating an opaque boundary known as the photosphere. Above this frequency, the plasma becomes transparent, allowing radiation to escape. The observed spectrum of Sagittarius A* rises smoothly through the millimeter range, and then declines toward higher energies, reflecting the balance between heating, cooling, and self-absorption within the flow. Time in this region behaves differently from elsewhere. To a distant observer, the motion of matter slows as it approaches the event horizon, red-shifted by gravity until it appears to freeze. To the matter itself, however, the fall occurs swiftly, the journey from the inner edge of the flow to the horizon taking only minutes. This contrast illustrates the relativity of perception. Near a black hole, what is rapid in local time becomes eternal when viewed from afar. Light emitted just above the event horizon can orbit the black hole multiple times before escaping, producing the characteristic photon ring seen in the event horizon telescope image. Each photon follows a path bent by gravity into near circular loops, creating the appearance of a glowing halo around the central shadow. The plasma also exhibits polarization, the alignment of light waves produced as they interact with magnetic fields. Measurements of polarization patterns reveal the structure and orientation of these fields near the black hole. The data show that the magnetic lines are ordered rather than chaotic, spiraling around the black hole in coherent patterns. This order implies that the magnetic field is anchored in the flow and may connect to the black hole's spin, influencing how energy and angular momentum are transferred. Polarized light therefore provides a map of invisible forces operating at the smallest observable scales. Variability remains one of the most intriguing aspects of Sagittarius A*. Observations over time reveal that its brightness changes on hourly timescales, corresponding to the orbital period of material near the innermost stable orbit. These fluctuations may reflect clumps of plasma or magnetic hotspots orbiting the black hole before being destroyed. By analyzing the timing and amplitude of these variations, astronomers can estimate the rotation rate of the black hole and test models of how matter behaves under such extreme conditions. The consistency of these fluctuations with theoretical predictions further reinforces the identification of Sagittarius A* as a spinning black hole governed by general relativity. Despite the violence of individual events, the overall luminosity of the system remains remarkably low. The black hole's efficiency in converting mass into energy is high, but the supply of mass is limited. Most of the gas flowing inward is lost to winds or fails to cool sufficiently to radiate. The faint light we detect represents only a minute fraction of the energy available from the accreted matter. Nevertheless, this small signal carries immense scientific value. Each photon escaping from near the event horizon provides information about gravity plasma physics and magnetic turbulence at the edge of known physics. On a cosmic scale, Sagittarius A* is quiet, but in its silence lies balance. The hot plasma orbiting the event horizon forms a bridge between the observable universe and the unknowable interior. It radiates just enough to outline the contours of space-time, offering a glimpse into conditions where light itself begins to bend back upon its source. The next step inward leads beyond observation to the threshold where the accretion flow ends and the boundary of the black hole begins. Their gravity triumphs completely, and even the fastest moving particles cannot escape. In that final region, matter ceases to emit light, and all description gives way to inference. What remains visible is only the glow from the edge, the last radiation before silence. Amid the quiet glow of Sagittarius, a star bursts of light occasionally disturb the calm. These sudden flares visible in X-ray, infrared, and radio wavelengths appear without warning and fade within hours. They are the black hole's rare, fleeting outbursts, windows into the hidden dynamics of its accretion flow. Though faint compared to the violent eruptions of quasars, these events reveal how magnetic and gravitational energy is intermittently released near the event horizon. They demonstrate that even a largely dormant black hole can awaken for brief moments, its silence broken by flashes of energy born in the turbulence of its hot plasma. The first evidence of such flares came in the early 2000s, when the Chandra X-ray Observatory recorded brief, powerful increases in brightness from the galactic center. Each burst raised Sagittarius A star's X-ray output by factors of hundreds, lasting typically 1 or 2 hours before returning to its usual faint level. Subsequent monitoring confirmed that these flares occur several times per day, though most are weaker than the first detected events. In parallel, infrared telescopes observed corresponding fluctuations in brightness, indicating that the same process drives both emissions. Later radio arrays detected slower variations following the X-ray flares by several hours, suggesting that the energy release propagates outward through the surrounding plasma before dissipating. The leading explanation for these flares involves magnetic reconnection. Within the accretion flow, twisted magnetic field lines store energy as they are wound by differential rotation. When the stress becomes too great, the lines snap and rejoin in new configurations, releasing energy that accelerates electrons to near-light speed. These relativistic particles emit synchrotron radiation as they spiral along magnetic fields, producing bursts of infrared and X-ray light. The timescale of the flares matches the orbital periods near the innermost stable orbit, supporting the idea that they originate just a few event horizon radii above the black hole. In some cases, multiple flares occur in rapid succession, implying a chain reaction of magnetic instabilities sweeping through the plasma. Each flare serves as a probe of extreme physics. The brightness and spectrum reveal the energy distribution of the accelerated electrons, while the timing between infrared and X-ray peaks constrains the size of the emitting region. The polarization of the light provides clues about the geometry of the magnetic field. Observations show that during a flare, polarization often increases, suggesting that the magnetic field becomes more ordered as it releases energy. This alignment fades as the plasma cools and turbulence returns. Such patterns offer a glimpse into the dynamic structure of space-time close to the event horizon, where magnetic tension and relativistic motion intertwine. The rise and decay of a typical flare follow predictable stages. At first, the emission brightens rapidly as magnetic energy converts to particle motion. The light curve then reaches a sharp peak before gradually fading as the electrons lose energy through radiation and adiabatic expansion. The total energy released in a single event is modest, roughly equivalent to the energy output of the Sun over several days, but concentrated in a region only a few light minutes across. The plasma heated by the flare may expand outward, forming a temporary bubble that emits in radio wavelengths as it cools. The observed time delay between the X-ray and radio peaks supports this model. High-energy radiation appears, first followed by longer wavelength emission from the expanding material. Infrared observations have added further detail. Instruments such as the Very Large Telescope's gravity interferometer can measure both the position and motion of these flaring regions in real time. In several instances, the source of infrared light has been seen moving in small loops around Sagittarius, a star tracing orbits roughly corresponding to the innermost stable circular path. These motions occur at speeds up to 30% of light, confirming that the flares arise from plasma clouds orbiting just outside the event horizon. The observed rotation direction matches the asymmetry seen in the Event Horizon Telescope image, implying that both trace the same underlying structure. The frequency and strength of flares vary unpredictably, but patterns emerge over long monitoring campaigns. Smaller flares occur daily, while stronger ones appear only a few times per month. Their occurrence may depend on the accumulation of magnetic stress or the infall of small gas clumps from the surrounding region. Occasionally, a cloud or fragment from a nearby star may cross into the accretion flow, triggering enhanced activity. When such material spirals inward, it compresses magnetic fields and injects fresh energy into the system, initiating a flare sequence. Once the disturbance passes, Sagittarius A returns to its baseline quietness. The colour and spectrum of the flares provide further evidence of their relativistic origin. In X-rays, the emission follows a power law distribution typical of synchrotron or inverse Compton processes, indicating that electrons are accelerated to extremely high energies. In the infrared, the spectrum is flatter, consistent with synchrotron emission from lower energy electrons in the same population. Some models suggest that as the plasma expands, the electrons lose energy adiabatically, causing the radiation to shift toward longer wavelengths over time. This explains why radio brightening lags behind X-ray peaks. Flares also offer a rare opportunity to measure time dilation and gravitational redshift near the black hole. The light from the orbiting plasma is stretched as it escapes the deep gravitational well, shifting toward longer wavelengths. When combined with Doppler effects from orbital motion, this produces distinctive asymmetries in the observed spectra. By fitting these shifts to models of general relativity, astronomers can infer the distance of the emitting region from the event horizon and estimate the spin of the black hole. Early analyses suggest that Sagittarius A rotates slowly, perhaps at less than half the maximum theoretical rate. Such measurements remain uncertain, but are gradually refining our understanding of how the black hole interacts with its surrounding matter. Occasionally, a particularly strong flare illuminates nearby gas, creating brief echoes of light known as reverberations. These reflections observed in X-rays reveal the structure of the inner accretion flow. The delay between the initial flare and its echo corresponds to the light travel time across the region, allowing astronomers to map distances and confirm the scale of the plasma's geometry. In this way, each flare becomes a natural experiment, sending out pulses of light that trace the invisible contours of the space surrounding the black hole. The relative faintness of Sagittarius A makes these events difficult to capture, but continuous monitoring has yielded a growing archive of data. Multi-wavelength campaigns coordinate observatories across the globe, combining X-ray, infrared, and radio observations to capture flares from start to finish. This synchronized effort provides a complete temporal picture of how energy evolves as it travels outward from the black hole's immediate vicinity. The observations reveal that even during its quiet phases, the environment near Sagittarius A remains dynamic and alive with microscopic eruptions of energy. The physics driving these outbursts applies universally to black holes of all sizes. What occurs near Sagittarius A on the scale of light minutes mirrors processes happening in active galaxies across cosmic distances, where similar reconnection and acceleration mechanisms power luminous jets. The difference is only one of scale and intensity. Our galactic center represents the quiet end of a continuum, a system operating at minimal fuel intake, yet governed by the same fundamental laws. The study of its flares thus bridges the gap between the calm nucleus of the Milky Way and the blazing hearts of distant quasars. Each flare fades quickly, leaving behind the faint glow of the persistent plasma. Yet every recorded event deepens the map of this hidden world. The irregular rhythm of activity alternating between stillness and sudden brightness defines the character of Sagittarius A. It is not a dead remnant, but a living system quietly breathing through pulses of energy. From these brief flashes, astronomers derive knowledge of conditions impossible to replicate elsewhere. The density of plasma, the strength of magnetic fields, and the geometry of space-time near a supermassive black hole. And as the flares subside, the glow dims again into the quiet background, guiding the view toward the even deeper region of warped light that surrounds the black hole's shadow, where the Event Horizon Telescope has captured the faint ring that marks the threshold of darkness. The first clear picture of the Milky Way's hidden heart emerged not from a single telescope, but from the synchronized cooperation of many spread across the planet. The Event Horizon Telescope, or EHT, was designed to create a virtual Earth-sized observatory capable of resolving the smallest and faintest details ever recorded in astronomy. It connected antennas across continents from Hawaii and Chile to Europe, the South Pole and North America, linking them through atomic clocks and precise timing systems, so that each recorded the same radio waves arriving from the galactic center. By combining these signals through the technique known as very long baseline interferometry, the collaboration achieved an angular resolution sharp enough to discern features just tens of micro-arc seconds across, roughly equivalent to seeing a golf ball on the surface of the moon. With this capability, humanity could finally observe the immediate environment of Sagittarius A. Capturing the image required years of preparation. Sagittarius. A star posed unique challenges. It is relatively small by cosmic standards, and the light it emits changes over minutes rather than days, meaning the scene evolves even as it is being observed. Earth's atmosphere distorts radio waves and weather conditions differ across observatories. To overcome these limitations, the EHT recorded vast amounts of data, simultaneously storing them on synchronized hard drives rather than transmitting them electronically. After weeks of observations, the drives were physically shipped to central processing facilities, where supercomputers correlated and combined the signals, reconstructing the faint interference pattern that encoded the image. The process demanded extreme precision. An error of a few trillionths of a second could blur the final result. Only through careful alignment and calibration did the hidden structure begin to appear. The image released in May 2022 showed a circular ring of golden light surrounding a dark center, a visual confirmation of a prediction made over a century earlier by general relativity. The ring represents radiation from hot plasma orbiting near the event horizon, its light bent by gravity into a nearly perfect circle. The central darkness is not the black hole itself, but its shadow, the region from which no light escapes. Photons emitted from behind the black hole are deflected around it, creating the illusion of a glowing halo enclosing an empty void. The brightness around the ring is uneven, with one side appearing more luminous. Due to Doppler boosting, light from material moving toward the observer is intensified, while light from material moving away is dimmed. This asymmetry reveals that the plasma rotates in a specific direction, confirming the presence of angular momentum and providing evidence that Sagittarius A star spins. The measured diameter of the ring corresponds precisely to what theory predicts for a black hole of 4 million solar masses. This match between observation and calculation provided strong validation of general relativity under extreme conditions. The agreement also confirmed that the mass estimated from stellar orbits and gravitational measurements was accurate, linking decades of indirect evidence with direct visual proof. The image of Sagittarius A star thus joined that of magnetism, the black hole in the galaxy Messier 87, which the EHT had revealed 3 years earlier. Together, these two observations demonstrated that the same laws of physics govern black holes across vastly different scales, from one measuring billions of solar masses to one only millions. The appearance of the image, though blurred, contains layers of subtle detail. Polarization maps derived from the same data reveal the orientation of magnetic fields around the black hole. These patterns form swirling arcs that follow the direction of the plasma's motion, showing that the field is highly ordered and likely plays a role in shaping both the inflow and outflow of matter. The polarization fraction. How much of the light is aligned indicates that the magnetic field is strong enough to influence the behavior of charged particles, supporting theoretical models that place magnetism at the core of the accretion process. Through these measurements, the EHT provided not only a picture but also a map of invisible forces sculpting the region. Behind the image lies a sophisticated process of interpretation. Because the data represent interference patterns rather than direct snapshots, reconstructing the picture required complex algorithms that filled gaps and removed noise. Teams around the world worked independently using different methods, comparing results to ensure consistency. Only when all reconstructions converged on the same ring-like structure did the collaboration confirm its authenticity. The brightness distribution, ring size, and orientation were then compared to thousands of simulated images generated from theoretical models. The best matches corresponded to a slowly spinning black hole surrounded by a hot magnetized plasma, consistent with other observations of Sagittarius A star. The image also reveals the immense difference in timescales between the two black holes observed by the EHT. The supermassive black hole in magnetism is about 1,000 times more massive, and its environment evolves slowly, allowing clear imaging over days. Sagittarius A star, by contrast, changes within minutes, so the observed ring represents an average over variable conditions. The plasma swirls and flickers during observation, blurring details but revealing dynamism. The challenge of imaging a living system at the threshold of light and gravity required algorithms capable of distinguishing structural stability from transient changes. This effort marks one of the most complex data analyses in astronomy's history. The faint glow captured by the EHT represents photons that have spent millennia traveling from the galactic center to Earth. Each photon followed a curved path shaped by gravity, looping around the black hole multiple times before escaping. What we see, therefore, is not a snapshot in the conventional sense, but a composite of countless trajectories compressed into a single pattern of brightness. The ring's existence proves that light can orbit a black hole in stable paths for brief periods before either falling inward or escaping outward. These orbits define the photon sphere, a boundary where space-time curvature traps radiation in circular motion. The shadow within the ring marks the point where even these trajectories fail, and light vanishes permanently from the visible universe. Beyond its visual impact, the image has deep implications for physics. It constrains alternative theories of gravity, many of which predict deviations from the shape and size observed. The remarkable match with general relativity confirms that Einstein's equations remain valid in the strongest gravitational fields known. It also establishes a baseline for future measurements aimed at testing deviations caused by spin magnetic coupling or surrounding matter. With more telescopes joining the EHT network, future observations will sharpen the image, potentially revealing motion within the ring itself. Detecting such rotation would allow scientists to measure the black hole's spin directly and understand how it interacts with the accretion flow. The visualization of Sagittarius A transformed an abstract concept into something tangible. For the first time, humanity could look upon the manifestation of gravity so strong that space folds back upon itself. The image is not dramatic in brightness, yet its quiet symmetry conveys immense power. It portrays a system in balance where matter, light, and curvature coexist in precise proportion. Every part of the Milky Way, from its spiral arms to its smallest fragments of dust, ultimately orbits this center. The faint ring of light seen by the EHT marks the physical anchor of our galaxy's structure. The work continues. The Event Horizon Telescope is expanding to include more observatories and to operate at additional frequencies, which will improve resolution and reduce noise. Polarization studies will refine understanding of magnetic fields, while time-resolved imaging may capture the evolution of plasma orbiting the black hole. Each improvement will bring the view closer to a true motion picture of the galactic center, showing how light bends and flickers under gravity's control. Future missions in space, free from atmospheric distortion, may one day image the ring without interruption, revealing how its brightness pulses and rotates with time. The image of Sagittarius A stands as a collective achievement of global science, the result of years of coordination and thousands of hours of observation. It connects technology, mathematics, and physics into a single act of discovery, turning theory into sight. In that faint ring lies the meeting of the known and the unknown photons dancing at the edge of an abyss, marking the boundary between visibility and oblivion. As attention moves still closer to that boundary, the focus turns to the shadow itself, the edge of darkness, where light bends completely around the black hole, forming the photon ring that defines the threshold of space-time. At the center of the Milky Way, hidden behind clouds of dust, and the slow motion of countless stars, the supermassive black hole known as Sagittarius A continues in silence. It does not blaze with the energy of distant quasars, or send out jets that pierce intergalactic space. Instead, it holds its position at the balance point of the galaxy, anchoring the rotation of 200 billion stars, while emitting only a faint, steady glow. Around it, gas drifts slowly in vast spirals, sometimes flaring with brief bursts of light before disappearing into darkness. The motion of everything, nearby stars, dust, and magnetic fields, unfolds under the influence of its gravity, each orbit tracing an invisible geometry shaped by space-time itself. The black hole's presence defines the structure of the galaxy, yet most of its life remains quiet. In that quietness lies stability. The surrounding stars continue their long revolutions, and the glowing ring of plasma near the event horizon continues to bend light into the faint circle seen by the Event Horizon Telescope. Every photon escaping from that region has travelled 26,000 years to reach Earth, carrying with it a record of conditions near the edge of the known. Through them, the centre of the Milky Way becomes not a void, but a visible form of gravity, a calm reminder that the universe's greatest forces need not be violent to be immense. Over cosmic time, Sagittarius A will endure as the stars around it age and fade. The galaxy's spiral arms will slowly change and its rotation will gradually shift, but the black hole at the center will remain gathering what the galaxy releases. Its silence is not emptiness but persistence, the still point around which all motion continues. The light that reaches us from its boundary is faint but steady, marking the edge between the luminous and the unobservable. To look toward it is to witness the balance of creation and collapse of motion and rest that governs the cosmos itself.